In this video, not only are we going to pay attention to how these two molecules will react, but we'll also pay attention to the stereochemistry of the end product. To do that, we have to pay attention to the stereochemistry of the things that we're beginning with. And this is just regular hydroxide anion. We've seen this show before. This is going to act as the nucleophile. It's not the strongest nucleophile. It's not iodide, but it's a pretty good nucleophile. So we have a good nucleophile here. Good nucleophile. We have a good nucleophile. And then over here, we have a carbon. It's not a methyl carbon. It's not bonded to a bunch of hydrogens. That would be a super fast Sn2 reaction. This guy could attack it. And it's not even a primary. It's a secondary. But we said, oh, if we have a pretty good nucleophile, this guy's going to want to give his electrons enough to that this will happen. It won't be the fastest reaction, but we can get an Sn2 reaction, especially if the solvent is the right type of solvent. And we'll talk more about this in future videos on what type of solvents are good for Sn2 reactions versus Sn1. So we're going to have an Sn1 reaction. We're going to have this situation. We're going to have this situation where one of the electrons from the nucleophile will be given to this secondary carbon. It's bonded to two other carbons, so it'll be given to the secondary carbon. And then that will allow this bromine to swipe the carbon that it was bonded with. And we know bromine's pretty electronegative, so it's going to do that. It's going to swipe that electron. And then at the end, you're going to end up with a bromine, or I should say bromide, now that it's an anion, a bromide anion. It swiped that electron. Before, bromine had 1, 2, 3, 4, 5, 6, 7 valence electrons. Now it's going to swipe this one over here, so now it'll have 8. 1, 2, 3, 4, 5, 6, 7, 8. Put a negative charge. It just gained an electron. And then what the other stuff will look like this. So that carbon, let me draw that carbon in the center. That's just like this. And notice bromine is leaving from the right, and the hydroxide is attacking, or it's giving its electron from the left, or it's bonding from the left. So what's it going to look like? Well, we have this, I guess we could call it this ethyl group coming straight out forward. We have this ethyl group coming straight out forward. We have this ethyl group coming straight out forward still, CH2, CH3. We have the hydrogen that is still going to be behind the carbon. So that hydrogen is still behind the carbon. So I could draw it like this. The bromine is no longer there. You still have this methyl group above it. So that is CH3. And now this hydroxide has attacked right in the same, I guess, direction that the bromine is leaving in, but from the opposite side. So that's leaving to the right. This guy's entering from the left. So then the hydroxide will be bonded like this. OH. Now, we just described a classic Sn2 reaction. This is a classic Sn2. And I always like to emphasize the Sn2 because my brain always confuses it with Sn1. So I always like to remind myself this is Sn2 because it is substitution with a nucleophile. That's the hydroxide in this case. And the number 2 says the rate determining step, and there is only one step in this reaction, involves both of the reactants. And this definitely is involving both of the reactants. So this is a classic Sn2. But the point of this video is to see what happened to the stereochemistry of this molecule. Obviously, it's a different molecule on this side, but did it switch from left to right? Or I guess we should say did it switch from R to S or S to R? Or did it stay in the same direction? So let's name this one using our naming mechanisms. Like you could call it the RS naming scheme. And then we'll name this one, and then we'll see if we switched our handedness. So first of all, let's just name the base molecule. And this is good review. So what's our longest carbon chain? We have 1, 2, 3, 4 carbons. And actually, I probably shouldn't have named it that way because this bromo group is closer to that end. So I should number it starting from here. We have 1, 2, 3, 4 carbons. So methyl is 1 carbon, ethyl is 2 carbons, propyl is 3 carbons, or prop is 3. So it's bute. Bute is 4 carbons. So it's going to be bute. It's all single bond. So it's going to be a butane. Butane. And on the number 2 carbon, we have a bromo group. So it's 2 bromobutane. 2 bromobutane. 2-bromobutane. And this is a chiral carbon, so we have to describe its handedness. And we know it's a chiral carbon because everything it's bonded to is different. This is bonded to 2 carbons, but this is a whole ethyl group. There's 2 carbons here. There's only 1 over there. And obviously, this is a hydrogen, and that's a bromine. So what's its handedness? And to do that, you want to put the group that has the lowest atomic number in the back. And we know hydrogen has the lowest atomic number, so it's already in the back. So that's convenient. We don't have to do any visualization of how do you rotate it, so you put it in the back. So that's already in the back. And then you just count from, you just start. So what we have in the front is this guy, this guy, this guy. And what you do is you start with the guy with the highest atomic number, and that would be bromine right there. And then you go in the direction, you go in a circle in the direction of the next highest atomic number. Carbon and carbon is a tie. The tiebreaker is that this carbon is bonded to another carbon, while this carbon is only bonded to hydrogens. So you're going to go in this direction right here. You're going to go clockwise. You're going to go, let me do that in another color. You are going to go clockwise. And the way I like to think about it is on top, we're going to the right. We're going clockwise. So this is R. S is to the left for sinister, R for the right. That's the way I think of it. So it's R. So this is R 2-bromobutane. So its handedness is R. Now what's this thing over here? What's this thing over here? Well, first of all, once again, we have 4 carbons. We have 1, 2, 3, 4 carbons. So but will be our prefix. But since the group that we are attached to is an OH group, it's a hydroxide group, this is actually an alcohol. So this is a little bit of practice of naming alcohols. So we still have but as our prefix. We still have but as our prefix, but we wouldn't call it butane. Since it has an OH there, we'll call it butanol. Butanol. And maybe I'll write that in blue to show that the anol comes from the OH. Butanol. Or maybe we could say the all comes from, maybe that's even better. Let me just write butanol. Butanol. That's a different color. Butan, and then the all comes from the fact that we have the OH there. We're dealing with an alcohol, and it's attached to the number 2 carbon. So we'll call it 2-butanol. 2-butanol. So we went from having 2-bromobutane to 2-butanol. But what is the handedness of this? So same exercise. You put the lowest atomic number in the back. That's the hydrogen. It's already in the back. And then you start with the atom, or the group that has the highest atomic number, or of the things that are bonded to this chiral carbon. It's still chiral. All of these things are different. You start with whatever has the highest atomic number. This oxygen has the highest atomic number. And you go in the direction of the next highest. This carbon and that carbon are a tie, but this one is also attached to other carbons, while this is attached only to hydrogens. So we go in this direction. We go in that direction, or counterclockwise, or in the sinister direction, or the leftward direction. So this is S for sinister, S2-butanol. So the whole point of this video is to show you that when you have an Sn2 reaction with a chiral onto a, I guess you could say, on a chiral carbon, that it changes the carbon stereochemistry. It changes its handedness. It went from, I guess you can view it as being right-handed to left-handed. It changes the way it's well, for lack of a better word, it changes its chirality. You could even imagine actually a situation where a bromine comes and attacks, and this bromine leaves it, and then you would actually have the same 2-bromobutane, but it would actually switch its handedness. And this is super important because this matters if you care whether or not you want to flip the stereochemistry or not. What we're going to see in the next video is, or maybe the video after that, is that in Sn1 reactions that you not only do you not flip your stereochemistry, that you kind of lose, if all of your molecules were of one handedness, your end product is going to be a mix of the two-handedness when you do an Sn1 reaction. But Sn2, you flip the handedness. You saw here we started with R, 2-bromobutane. Sn2 reaction happened. We ended up with S. And it makes complete sense. You view this, this is coming from the back, so you view this as kind of an umbrella, right? This was kind of an upturned umbrella. This was the handle. And when this comes in, he becomes the handle, and the umbrella flips in that direction. So that's one way to think about it. So visually, it also should make a little bit of sense.